Hello again, this is Alister McGrath at Oxford University. In the last presentation we looked at how we develop ways of making sense of our world. How do we generate theories? But the point I'm going to make now is that very often we find we have several possible explanations of our observations. Not just one possible explanation, there may be many possible explanations. So we have to decide which of these is the best explanation. So the question then becomes, how do we decide? What criteria do we use to determine which is the best explanation? And here's another question. Is the best explanation a true explanation? It's an important question because the history of science makes it very clear that theories that were once regarded as highly credible in the past are now simply discarded. Here's a quote from Arthur Koestler that I think makes this point very effectively. Listen to this. "The progress of science," he writes, "is strewn like an ancient desert trail with the bleached skeletons of discarded theories, which once seemed to possess eternal life." Now, the point I want you to appreciate here is that scientists may judge a certain explanation to be the best at the present moment, but that doesn't mean this judgment is true. Why not? Well, you see, additional evidence may become available, calling that explanation into question. So what one scientific generation regards as being correct might be abandoned or modified by later generations, and there are lots of examples of exactly that happening. So I'm going to explore with you the scientific reasoning process that's now widely known as inference to the best explanation. Now, this specific approach was set out using that name in a lecture of December 1963 by the philosopher Gilbert Harman. Now, I want to make a point that although Harman named it, you'll actually find this approach being used, for example, in Charles Darwin's Origin of Species in 1859 and other works before this. The point is this: inference to the best explanation recognizes that there are several possible explanations for any set of observations. So you identify what the possibilities are, and then you try to identify criteria of judgment you might use to figure out which of these possible theories is the best. And Harman points out that you don't actually need to be able to prove a theory is true. You need to be able to show it's better than its rivals. So what criteria might we use to evaluate competing theories? Well, there are three that are widely used. Let's look at each of them very briefly. First of all, simplicity. And in the later Middle Ages, William of Ockham, a well-known medieval philosopher, recommended avoiding unnecessary hypotheses. Keep things simple. And this principle is often known as Occam's razor, or more technically as the principle of parsimony. In other words, simplicity is a guide to truth. And that's true. But it's only a guide, because although it's true the simplest theories are often the best, they are not always the best. For example, think of Copernicus's model of the solar system. It was elegantly simple. It asked us to imagine the Earth revolving around the Sun in a circular orbit at constant speed. Very elegant, very simple, but wrong. It failed to account more accurately for observations of the movement of the planets than the older Ptolemaic model, because it was wrong. The Ptolemaic model sure said everything orbits around the Earth. Copernicus said everything orbits around the Sun. But you see, everything orbits around the Sun, not in mathematically simple circles, but in more complex ellipses and at variable speeds of motion. In other words, it's not simple. Once Copernicus' theory was made more complicated, it actually made much more sense of what was actually observed. So the point you just need to appreciate is this: simplicity may point to truth, but it doesn't guarantee truth. So that was the first criterion, simplicity. What about others? Well, the second one we're going to look at is elegance and beauty. And the point that many philosophers of science make is that successful theories are often very elegant. And back in 1955, the physicist Paul Dirac was asked to set out his philosophy of physics. And here's what he said: physical laws should have mathematical beauty. And it's a really interesting point. Is a beautiful theory more likely to be true than one that doesn't seem quite so beautiful? And for example, Dirac pointed out that Newton's classical mechanics were simple, but Einstein's relativistic mechanics were more complicated, but they were much more elegant mathematically. Again, a very important point. It's hard, however, to see why such a subjective criterion of beauty should be an indicator of truth, because after all, beauty is a very subjective matter. It varies from one individual to another. But nevertheless, there's something there. Some philosophers say, look, maybe it's not beauty as such, but beauty as an indication of, for example, simplicity, which is what's at issue here. Well, that's possible. But let's look at our third criterion, a capacity to predict. And many scientists would argue it's essential a scientific theory ought to be able to predict things you can check out. And Einstein's theory of general relativity is a very good example of an innovative theory which made unexpected predictions that were subsequently confirmed. Some would say, well, that's very nice, but why should the capacity to predict be so important, apart from the psychological impact of the confirmation of a novel prediction? I mean, let's go back to Darwin's theory of natural selection. And one of the points that Darwin was absolutely clear about was that his new theory made no testable predictions. However, he said, look, I'm still sure this is right because it explains things so plausibly, so well. It didn't predict anything, but it was better at explaining existing observations of the world than the other theories that were around at the time. So that's science. What about religion? Well, you know, there are parallels within religion to these scientific questions about theory choice. Let's look at the philosopher Richard Swinburne, who I think illustrates this point very, very well. Richard Swinburne argues that the existence of God can be seen as the best explanation of what we observe in the world when it's seen as part of a larger cumulative case. And for Swinburne, the existence of the universe can be made comprehensible if we suppose it is brought about by God. And Swinburne argues that the existence of our universe is something that needs to be explained. It's not just a kind of brute fact we have to accept. We want to know why there is something rather than nothing. And Swinburne says, well, there are two possible explanations. First, science can provide a natural explanation for the existence of the universe. Or second, the universe and everything in it we observe exists because of the intentional causal activity of a personal God. Now, interestingly, Swinburne does not see himself as having to prove God's existence. He sees his job as being to show that the existence of God makes more sense of our observations and experiences than alternative theories like materialist naturalism. And Swinburne's argument is that he has shown that belief in God is more probable than rival theories. And that's all he needs to do. And that, of course, does lead us into a really interesting question. Can we actually prove a theory such as the existence of God is right? I think that's really interesting. So let's move on in the next presentation to start thinking about proof in science and religion. I look forward to speaking to you again very soon. Thank you so much for listening.